So it's a pleasure to have Plavnik here from IU, and she will talk to us about gauging, condensation, and zesting of quantum symmetries.
Thank you, Didma, for the introduction, and thank you to the organizers for putting together this great meeting. So before starting, maybe a disclaimer. Let's think that I will talk about zesting probably as a quantum symmetry, and I might mention something about gauging and condensation at the end, if time allows. And this is based on joint work with my collaborators, Colin Delaney, Cesar Galindo, Eric Rowell, and Ching Zhang, and also some work with Colin Delaney again and Sang Kim during an RU project at IU. So let me fix some notation before we start. So what I will talk about are these topological orders that were mentioned yesterday in some talks, and specifically in two-dimensional things. So anion systems in two-dimension, bosonic two-dimensional topological phases of matter. So I will be talking basically about these modular categories that were already mentioned. And the idea is that I will be doing some constructions or telling you about some of the constructions. And some of the things that I'm interested when I'm looking at these modular categories are looking at these simple objects or anion types. We look at how many of these anion types we have, and we like to know how they fuse, right? So these are the fusion rules that I will usually encode in these matrices, these fusion matrices. This is not the whole information. We do need some associativity constraint that it's encoded in the 6 symbols or in the F matrices. And we have a unit. Do you want to?
Yeah. You're talking about. Oh, just have the microphone so it's not on your skin yet. Okay.
Thank you. Okay. So we want to have also a braid that it's this particle interchange that will tell us that this tensor product that we were looking at is commutative. And we have twists. This is very useful. We have a trace associated. It's a nice twist that give us a trace, and it's encoded in this way. And these two things give us two nice matrices that are called the modular data, these S and T matrices that are very nice and give us projective representations of the modular group and have a lot of nice relations. So this is the kind of things that I will be looking at, these modular categories and all these invariants associated to them. So let me tell you some motivating questions to look at these constructions that I will mention later. So some of the problems that I'm thinking of, and some people in the field are thinking of, are classification, for example. So we like to classify by looking at different invariants, different of these things, for example, the number of simple objects, this rank, or there are notions of dimensions, quantum dimension or Frobenius-Perron dimension, and we also classify looking at that. The idea is that we would like to have some kind of periodic table of these modular categories, and Colin Delaney usually has this beautiful diagram there or picture there of the idea. And some of these invariants you can detect from other of the invariants. For example, with the S matrix, we can get the fusion rules, but some invariants are easy to look and sometimes it's easy to distinguish directly from them. We would like to know what kind of invariants we need, and when we have them, we would like to have a list, right, of the possible categories given certain invariants. So other things that we look sometimes are these fermionic topological phases of matter versus these bosonic ones, so modular categories versus supermodulars or these spin modular categories. And this is related to this 16-fold wave of Kitaev, and I will say a little bit more about this in a couple of minutes. But let me say that this zesting construction appeared first, or we detected first in these two settings. So in 2012, we were trying to classify, or we were classifying modular categories of certain Frobenius-Perron dimension, specifically 36, dimension 36. And we found some nice fusion ring, maybe exotic at this time, but related to another one that we knew. And I will give an example, or I will tell you that example in the next slide. And we wanted to know how they are really, or if they were really related. They looked similar, but how they relate. And that was the first time that we saw the zesting construction. And then when we were studying this spin modular category, so the modular closure of supermodular categories, we again so that we could realize these modular closures using Zesting. Or if we have one of them, we could get new ones of them using Zesting. So that's the first time that we saw Zesting. We did it in that specific settings, and then we generalized that construction, or we gave maybe a more organized construction using some cohomological data. So that's what I will tell you in a little bit. And this construction was useful in other settings. For example, when we are looking to categorification or realization questions, for example, I told you we have these beautiful fusion matrices, but that are not enough to describe a fusion category. We also need these 6J symbols, these associativity constraints. So sometimes we start with a fusion ring and we want to know if it comes from a fusion category, and there are different tests. And one thing that it was useful, the Zesting was in 2012, and in 2019, some people categorize some fusion rules or fusion rings using Zesting. From things that we knew, we use the Zesting and we get these other fusion rings that we didn't know if they existed or we didn't know if they came from a fusion category. And the same with modular data. Some people get these nice pairs of S and T matrices, and we want to know if they really come from a modular category or if they just have nice properties. And again, in 2019, some of these example came, and I will give you more details in a little bit. And then coming back to this idea of this periodic table, like Shenhan was saying yesterday, we want some complete invariants sometimes. So there is this idea of modular isotopes. What happens if you have, or modular isotopes are inequivalent modular categories that have the same modular data up to relabeling. So that was one of the comments yesterday, that this modular data was not enough. It was not a complete invariant. So it's a nice invariant, but it's not complete. So we want to understand these kind of families that are related because they have the same modular data, but they are not equivalent. So we use knots and link invariants and Zesting to relate some of the known families of modular isotopes that we have. So this is the example that I was mentioning that we found in 2012. This is a nice example of a modular category coming from a quantum group. And sorry, here should be a 3, not an N. So we were looking at these Frobenius modular categories of dimension 36, and we found two fusion rings with 10 simple objects. So rank 10 fusion rings. One of them was known and was coming from this quantum group category and has this fusion graph. And we saw that we could organize our simple objects in certain or label them by certain group elements. This gave us in this category some set 3 grading. And we saw that the other one, the exotic one, could be obtained from this one if we twist a little bit our associativity constraint and our fusion rules using some abelian anions. So we got this using Zesting. So it's a very a small change that we were doing. We were just multiplying or changing these matrices via these invertible objects or abelian anions, but we get a very different fusion ring. And there are very big changes that happen. For this component is fixed, but some things that happen are, for example, the dual, the antiparticle change a lot. It's a different thing. In this one, when you do x to the cube, so you tensor x three times, you get the unit inside of it, and in this one it doesn't. So it have different duals, and you can see that it's a different, quite different thing, but it's not that bad. We can get one from the other. So that was the first time we saw it. And then I was telling you that in this other context of studying these supermodular categories, we also saw Zesting emerging there. So Kitaev's 16-fold will tell us that if we have the category of super vector spaces, there are 16 modular closures. So there are 16 modular categories that have a supervect inside, and that the dimension is 2 times the dimension of this category. So this has dimension 2, these are modular categories of dimension 4. 8 are Ising types, and 8 are pointed. Pointed is just that they are abelian theories. So there was a question if this was true in general for supermodular categories. A supermodular category is a category that has transparent objects given by this category, while in the modular category, we will just have vec. In this case, we have supervec. So there was this question if this was always true for supermodular categories, that always you can have exactly 16 modular categories that have your original category inside and has the double of the dimension. And so there was some progress on this. There was work of Davidov, Muger, Nikshik, and Ostrich, and also work of Lian and Zhao Wen. And they show that if there is one of these minimal modular extension, there is exactly 16 of them. And then with some of my collaborators, we show that actually this 8 and 8 is not a coincidence. You have always 2 orbits of minimal closures, and they are all related to orbits under Zesting, basically. So you have 8 of them given by Zesting one of that minimal modular closures, and 8 of them by Zesting some other of the closure. So you can always get the 16 one, and you can organize them using Zesting. And there is progress on the answer of the existence of these things by Theo Johnson-Frey and David Reuter. They prove the existence in the case when you are not interested, at least in this ribbon structure. So they have progress on that. But it was interesting to see, and we could compute explicitly if we have one minimal modular extension, how to get the others using Zesting. So that was the other time we saw Zesting. So let me tell you, roughly speaking, what is this Zesting construction. So I will start with some A-graded fusion A-graded braided fusion category. So what is a grading? I will organize my objects like I was doing in the SU3 level 3 example. So I will partition the simple objects in certain blocks, let's say labeled by group elements. In this case, the group will be abelian because I'm in this commutative setting. But these need to play this block decomposition, let's say, or this direct sum decomposition need to play nicely with our tensor product. So if I tensor something in this component and this component need to get into the component labeled by the product in the group of these elements. So what was the idea? As I told you before, we want to modify slightly. We want to add a little bit of flavor to our fusion rules by tensoring with an abelian anion or with an invertible object. So if we have an object in the A-graded component and in the B-graded component, the new tensor product is the original tensor product tensor some invertible object that it's just determined by the labels here. It doesn't depend on the object specifically, but just on the labels. This is an invertible object, and also we ask that this object is in the trivial component of this grading. So meaning that it's in the component labeled by the identity of, or the neutral element in my group. We also ask some normalization things. So this thing here, if I plug something in the trivial component, this will be a unit. So there is some normalization, and we do the same. So here I only told you what to do with the fusion rules, but if you have this change these fusion rules, you will need to modify also the associativity constraint in a way that still satisfy our nice axioms, the pentagon axiom. And I want also to be able to modify the braid. And if I'm in a pivotal or ribbon, I also want to be able to modify the twist. So this construction is not explicitly for modular categories, but we can apply it to modular, and we know when we get a modular category back. It's not like you always get modular, but we have control under that. So I will not give you all the details on the construction, but one of the things is that when we want to construct the Zestit associativity, what we do is we get a two co-cycle condition, maybe let me say here, a two co-cycle condition in this function lambda that I was using, this lambda that takes two elements in my group and give me back an invertible. So it has a two co-cycle condition, and I use this to define my new associativity. To define the new braid, we keep the old braid, and the only thing is that now will appear in the tensor these invertibles. So we pick a family of certain isomorphism between these things, and that will give us the Zestit braid. So we just deform a little bit the braid by this phase, basically, that depends on the A and B. But as I mentioned, there are some conditions that this associativity and this braid need to satisfy: the pentagon axiom and the hexagons axioms. And these new pentagons and these new hexagons can be solved, or they will give you a condition that it's basically at the level of this morphism here and of this and this in the level of the braiding and the hexagons here. So we have some abstractions for this construction to really give you a new fusion or a new braided category. And these are cohomological restrictions or obstructions. So I was telling you that we are interested usually if I have fusion rules or fusion ring, or if I have S&T matrices, I want to know if they really come from a fusion category or a modular category, depending on the case. So for example, one time that we used the Zesting was this 2012 paper that I was telling you. We were able to show that they were related by Zesting, these two things. So we show the existence of that fusion ring in that way. But also Liu, Palku, and Ren, using in 2021, they were studying fusion rings with multiplicity 1 and rank up to 6. And some of the fusion rings, they were able to realize them, or they proved that they came from fusion categories using Zesting. And in 2018, Pinchas Grossman and Masaki Izumi, they presented a lot of families of S&T matrices of modular data. And the question was, do they come from some modular category or not? Specifically, there were some rank 10 modular tensor categories that they knew that they didn't come from centers, but in work of Bonderson, Rowell, and Shenhan Wang, they show that families could all be recovered. The 16 pairs of modular data, they were recovered using Zesting and applying it to the center of the half of the E6 theory. And this, if I'm remembering correctly, actually uses the same construction that I was telling you for the supermodular setting, this idea of the orbit. So they recovered using Zesting of this and also the conjugate of this. So I was telling you a lot about this periodic table and this idea of looking into invariants. So what happened with the invariants when we zest? That's a question that we were looking. We wanted to see how dramatic zesting change it or could change your category. So as I was saying, we only do changes in the fusion rules, in the associativity. We don't really change how we decompose these blocks in my graded category. So for example, the rank is unchanged. The Frobenius-Perron dimension depends on the fusion matrices, but since I'm only modifying them by an invertible object, which is it's an abelian anion, but it's characterized also for having dimension 1, or Frobenius-Perron dimension 1. The Frobenius-Perron dimension of the simples or of all the categories don't change, so all this doesn't change. The grading doesn't change by definition, actually. So all this data is preserved, so all this first part of the table is preserved. We know how the fusion rules change, so that's controlled, because that's how we define the construction. And actually, we found nice formulas for the new trace. And using the new trace, you can see how the modular data and how the braid group image change. So we have very nice formulas for this. Then in the examples of the 16-fold way, actually, we could see that the central charge changed. In these 8 examples, all these 8 things that were related by Zesting, they all have different central charge, and therefore also the width class change. So these things can change under Zesting. They not always change, but in many cases they do, specifically in this super setting. And then we also studied lately the knot and link invariants. And let me say something else. I was telling you that we have this grading that doesn't change. Actually, it's more than just like this grading is like I was adding defects in my theory. The defects don't change, but what it changes is how I fuse the defects between them. So the module category doesn't change itself. It's how they do the product between these modules. So let me tell you a little bit about these modular isotopes examples. So as we were saying, these S&T are not enough to distinguish modular categories. For example, in 2017, Mignard and Peter Schauenburg gave examples using the double of groups. So they have this group, the semi-direct product of set Q and set P. P need to be bigger than 3. Both are odd primes, and P divides Q minus 1. And what they show is that there are p different modular categories, and this depends on this cocycle here. There are p different choices for that, but there are only 3 sets of modular data. So some of them share the same modular data. The smallest example is when P is 5 and Q is 11, and that already has rank 49. So we will be dealing with 49 anions, right, or simple objects. What we proved with Colleen and Sang was that actually this family is all related by Zesting. So if you start with just the trivial cocycle here, you can get to any of them using the Zesting construction. And that was useful because, so other thing that happened when these examples came out, or when people realized that these are not complete invariants, people started studying what other links or not invariants could give us, or could distinguish at least this family, right, or at least this family. So some people studied the Whitehead link or the Borromean tensors. And what we did here was thinking on that, because that will, or some of these distinguish this modular isotope. We wanted to know what happened with the knots and link invariants under Zesting. So basically, I mean, I will not go into deep details here, but basically we saw how this Markov trace of this braid word change under Zesting. And what it's interesting is that actually it decouples. So basically you get the same link invariant up to some phase here. The phase depends on the grading, the elements that I was saying that you use to label your blocks. And this is the Zesting data. So it changed using the grading and the Zesting data. But basically, just changed by a factor. So it decoupled nicely. And what we used to prove that all this family was related by Zesting, we used a couple of different things, but one of the results is that we can compute very nicely how in this case, which is called cyclic Zesting, the Borromean ring, or the invariant coming from the Borromean rings and from the Whitehead link change, and they distinguish this family. So we were able to use that. So also motivated by this question, or by this, maybe let me go back 1 second to point out something. This here is actually, you can see it also as the center of a family of fusion categories. And these are abelian theories coming from the group and a cocycle. So actually, when we were doing the Zesting, the only part that helped us distinguish was doing Zesting at this level, at the level of the fusion category that later we were taking the Drinfeld center of. So we thought, okay, is this true that if we have a Zesting in, and now I come back here, so we wanted to know how Zesting relates to other construction, for example, the Drinfeld center. So in this particular case of the Mignard-Schauenburg example, given a Zesting of the category, that Zesting induced a Zesting on the centers. But this is not always true, and this is basic. Some examples are also kind of easy to see that this is not true, because sometimes this original center could be pointed, and if you zest or an abelian theory, and if you zest an abelian theory, you stay abelian. But when you set the original category and take the center, you can get something non-abelian. So it was easy to see that it's not always true. But this case that we were studying was nice because I was telling you that was cyclic. So cyclic means that the labels that I was taking actually were a cyclic group, not just an abelian group. And if you are doing cyclic Zesting, this is always true. You do have this. And this is work of Aguilar, a master thesis of this year, Cesar Galindo student. So, and it's a nice result, and she has some other details about how the Drinfeld center plays with the Zesting. Other construction that we were interested in was the gauging construction. For this, you need to start with certain categorical action in your category. What we saw is that many modular categories can be realized both as a Zesting of certain category or a gauging of a different one. So for example, when you're in the case that the trivial component or the invertible elements, the abelian anions in your trivial component are of the form rep G, so this gives rise to some nice commutative algebra, then all modular Zestings, and here it's important that I take the word modular, all the modular Zestings of my original category can be realized using gaugings of this condensation here. So this is one case, and why I like this, because I think that maybe, so gauging and Zesting are different, and I will say a couple of words in a second, but maybe using this thing that sometimes you can realize it in these two different ways, we can learn from the category in different ways. Like some things are very easy to compute using Zesting and hard to do via gauging. So that's what I will say here. There are other interesting constructions that I didn't have time to talk. For example, the relative tensor product or the condensation. Like sometimes Zesting can also be seen in some cases as condensation by a diagonal algebra that you can get. So what are the pros and cons or the difference of this construction? In these two examples, in gauging and in the relative tensor product or in the condensation, a lot of the structure comes from free, because you know that things will work. For example, gauging is always, if it exists, it's always modular, while Zesting, no. Zesting can change dramatically that. You can start with something modular and end with something symmetric. So it's kind of very drastic in that sense, even if we know we have a computation on how these transparent objects change, so we know the description. Gauging, for example, always preserve the width class and the central charge, thing that we know that Zesting doesn't. So this is not true for Zesting. We know how these change under condensation, so that's very different. But these two constructions usually are hard to compute, or some of the data, it's very hard to compute. Even fusion rules for gauging is hard. Modular data, even much harder. The advantage of Zesting is that we have very explicit formulas for many of the things: fusion rules, modular data, braid image, link and not invariants, and usually all the data is basically controlled by cohomological data by characters and some cohomology classes. So that's nice, and it's very easy to compute examples, while here sometimes that's hard. One of the maybe cons is that Zesting is not the most general construction. This is a particular case of this theory that we listened yesterday from Chen Han of extension by Tinkoff, Nikshik, and Ostrich, and also by Davidov and Nikshik in the braided case. So it's not the most general. The advantage is that it's very computable. That's what I would say. So I don't know if you have comments or questions, and thank you for listening.
Get the experts to say something.
You won't get lunch until there's this. Yeah, sure.
Hi, this is Sean Cui. I'm definitely not an expert on this, but just want to ask a basic question. Have you thought about generalizing this to G-cross testing, like when the group is non-abelian, basically, when the grading group is non-abelian?
Yeah, so yeah, we thought about the first part. You can do it even for fusion categories in general, and you don't need abelian there. I was doing braiding because it's slightly more general and you can change more things. But we are also thinking on the G-cross setting, starting with a G-cross and see if basically getting a new G-cross out of it. And there is also work by Parsa Bonderson and David Eisen and Christina Knapp on this direction. But things seems to work fairly well in that G-cross setting also, and get the G-cross modular data and some things. This should be out soon, hopefully.
Okay, that's great. Thank you.
Yeah, and actually, some of these things I said, there are obstructions. So when you do the braided settings, sometimes you, in the SU3 level 3 example, some of them don't admit like some of the cocycles that you can construct, they don't banish the obstructions that they get, but that give you a G-cross. So that's one of the motivations. Try to understand what happened when we do the G-cross in these things that don't allow us to do the regular associative braided. So yeah, in that context. Thank you, Sean.
Thank you.
Any other questions? If not, let's thank Julia again.